Have you ever noticed how some places on Earth feel shaped by forces so powerful or precise that they seem almost unreal? In this episode of Unearthed Secrets, we explore stone towers carved by erosion, living volcanoes, painted mountains, drifting continents, and hidden worlds beneath the ground. Before we begin, like and subscribe, and tell us in the comments where you're watching from and what time it is for you right now. The stone that grew into towers. In the heart of central Anatolia, where dry plateaus stretch beneath wide skies, the land rises into shapes that seem deliberate, almost architectural. Tall stone columns stand crowned with darker caps. Some resemble sentinels. Others look like mushrooms, spires, or figures frozen mid-motion. They cluster in valleys, line ridges, and emerge suddenly from otherwise flat ground. At first glance, they feel artificial, as if carved by design rather than chance. These are the fairy chimneys of Cappadocia, one of the most distinctive geological landscapes on Earth, shaped entirely by volcanic fire, erosion, and time. The Cappadocia fairy chimneys are found across the Cappadocia region of Turkey, particularly around Göreme, Paşabağ, Monks Valley, Zelve, and Uçhisar. The formations vary in size and shape, but they all share a common origin rooted in volcanic activity millions of years ago. Cappadocia's story begins not with stone, but with fire. Between roughly 10 and 3 million years ago, a series of volcanic eruptions reshaped central Anatolia. Volcanoes such as Erciyes, Hasan, and Golida erupted repeatedly, blanketing the region in thick layers of ash, lava, and volcanic debris. Over time, ash deposits accumulated hundreds of meters deep. This ash hardened into tuff, a soft, porous volcanic rock. In some places, lava flows followed, spreading across the ash and cooling into harder basalt. These lava layers formed protective caps over the softer tuff below. At the time, the landscape was relatively flat, layered like a cake of different materials. The transformation into fairy chimneys began much later. As volcanic activity ceased, erosion took over. Wind, rain, temperature fluctuations, and occasional flooding began to wear away the exposed tuff. Because tuff is relatively soft, it erodes easily. However, where harder basalt caps existed, the underlying rock was shielded. This difference in resistance created vertical structures. The surrounding softer material eroded faster, while protected sections remained standing. Over hundreds of thousands of years, tall pillars formed, topped by harder stone, creating the classic fairy chimney shape. Each chimney represents a balance between protection and exposure. Where the capstone remains intact, the pillar survives. When the capstone breaks or falls, erosion accelerates, and the structure eventually collapses. This process is ongoing. Cappadocia's fairy chimneys are not static monuments. They are temporary forms in geological terms. New ones continue to emerge, while older ones crumble and disappear. The landscape is constantly reshaping itself, even if change is imperceptible within a human lifetime. What makes Cappadocia exceptional is not just the formations themselves, but their scale and density. Fairy chimneys appear across entire valleys, forming forests of stone rather than isolated features. Some reach heights of more than 40 meters. Others are squat and rounded. No two are exactly alike. The colors vary as well. Tuff ranges from pale beige to pink, ochre, and gray, depending on mineral content. Light shifts these tones throughout the day. At sunrise and sunset, the formations glow warm red and gold. At midday, they appear pale and chalky. After rain, colors deepen, revealing layers and textures normally hidden. But Cappadocia's fairy chimneys are more than geological curiosities. Humans have lived among them for thousands of years, and changed how they are perceived. Because tuff is soft and easily carved, ancient inhabitants discovered that the chimneys and surrounding rock could be hollowed out using simple tools. As early as the Hittite period, people carved chambers into the stone. Over time, these evolved into homes, storage rooms, chapels, monasteries, and entire underground cities. Early Christians seeking refuge from persecution during the Roman era expanded this practice. They carved churches directly into the fairy chimneys, decorating interiors with frescoes that survive to this day. The chimneys became places of worship, isolation, and safety. In valleys like Göreme and Zelve, entire communities existed within the rock itself. Above ground, the landscape looked empty and strange. Inside, it was alive with daily activity. This dual identity, natural formation and human shelter, sets Cappadocia apart from other eroded landscapes. The fairy chimneys were not merely observed, they were inhabited. Some chimneys still show signs of this use: doorways cut into narrow pillars, small windows opening onto nothing but air, stairways carved into stone walls. These features did not alter the fundamental shape of the chimneys, but they changed their meaning. From a distance, Cappadocia looks surreal. Up close, it feels intimate. The region's climate played a key role in making this possible. Cappadocia experiences hot, dry summers and cold winters. Rainfall is limited, slowing erosion enough that carved structures could last centuries. At the same time, temperature differences between day and night cause gradual cracking, continuing the slow reshaping of the landscape. Water remains the primary sculptor. When rain falls, it flows through narrow channels between chimneys, undercutting bases and widening valleys. Occasional flash floods accelerate erosion dramatically. Wind carries away loosened particles, polishing surfaces and sharpening edges. Freeze-thaw cycles add another layer of change. Water seeps into cracks, freezes at night, expands, and fractures the rock. Over time, this process weakens capstones and pillars alike. The fairy chimneys exist because all these forces align. Not too much rain, not too little wind, not too rapid erosion. Change the balance, and the landscape would look entirely different. Scientifically, Cappadocia is a textbook example of differential erosion. It demonstrates how landscapes are shaped not by a single force, but by interactions between material properties and environmental conditions. The chimneys also preserve a record of volcanic history. Layers within the tuff reflect different eruption phases. By studying these layers, geologists can reconstruct the region's volcanic past. Culturally, Cappadocia has been known and described for centuries. Ancient writers remarked on its strange rock forms. Travelers along early trade routes passed through its valleys. Yet the formations remained difficult to explain before modern geology. The name fairy chimneys reflects this mystery. It suggests something otherworldly, shaped by unseen forces. In folklore, these towers were imagined as dwellings of spirits or supernatural beings. While the explanation today is scientific, the sense of strangeness remains. Modern tourism has transformed Cappadocia into one of Turkey's most visited regions. Hot air balloons rise at dawn, floating above the valleys and chimneys, offering a view that reveals their full scale. From above, the formations resemble waves frozen in mid-surge. This popularity brings challenges. Foot traffic, development, and vibration affect fragile rock. Conservation efforts aim to protect the landscape while allowing access. Some chimneys have collapsed in recent decades, reminders that these formations are not permanent. Cappadocia is now a UNESCO World Heritage Site, recognized for both its natural and cultural significance. Protection focuses not only on the chimneys themselves, but on the broader system that sustains them. At night, Cappadocia quiets. The valleys empty. Wind moves softly between stone towers. Shadows stretch long under moonlight. The chimneys lose their playful appearance and become silhouettes, ancient, still, and watchful. In these moments, it becomes easier to understand why humans once sought refuge here. The stone absorbs sound. The landscape encloses rather than exposes. Even today, it feels sheltered. The fairy chimneys do not rise because they were built upward. They exist because everything around them was worn away. They are survivors of erosion, not monuments of construction. Each chimney stands as a measure of time, how long its capstone has held, how slowly water has worked, how patiently wind has carved. Their shapes are accidents refined by repetition. Eventually, every fairy chimney will fall. Capstones will crack. Pillars will thin. Valleys will widen. The landscape will change again, taking forms not yet visible. But for now, in central Turkey, stone still stands in improbable towers, formed by fire, shaped by air and water, and adapted by human hands. Cappadocia's fairy chimneys remind us that some of the most extraordinary landscapes are not created in moments of violence, but through quiet imbalance sustained over immense time. Not carved with intention, not built with purpose, but revealed, slowly, patiently, by the earth itself. The crater that never stays still, high in the cloud forests of central Costa Rica, Where mist drifts between moss-covered trees and the air smells faintly of sulfur, there's a volcano whose surface is never truly at rest. Steam rises constantly from its depths. Gas hisses from unseen vents. At times, the crater holds a lake of brilliant turquoise acid. At other times, that lake vanishes entirely, replaced by ash, rubble, and exposed rock. This is Poás volcano, one of the most active, closely monitored, and scientifically revealing volcanic craters in the world. The Poás volcano sits within Poás Volcano National Park, roughly 40 kilometers north of San Jose. Rising to about 2,700 meters above sea level, Poás is not Costa Rica's tallest volcano, but it is among its most accessible and unpredictable. Unlike many volcanoes that remain dormant for centuries, Poás is defined by constant change, small eruptions, gas releases, shifting crater lakes, and rapid transitions between calm and violent activity. At the center of Poás lies its defining feature, one of the largest active volcanic craters on Earth. The main crater measures approximately 1.5 kilometers wide and 300 meters deep, a vast open depression carved by repeated eruptions and collapses over thousands of years. Poás is a stratovolcano, built up over time through layers of lava, ash, and volcanic debris. Its formation is tied directly to tectonic forces shaping Central America. Along Costa Rica's Pacific coast, the Cocos Plate is being forced beneath the Caribbean Plate in a process known as subduction. As the descending plate heats and melts, magma rises through fractures in the crust, feeding volcanoes like Poás. This process has been ongoing for millions of years, creating a chain of volcanoes across the country. Poás is one of the most active expressions of this system. What makes Poás exceptional is not just its activity, but how exposed that activity is. The crater is open and easily observable, allowing scientists to study volcanic processes in near real time. Gas emissions, seismic signals, lake chemistry, and deformation of the ground are monitored continuously. Few volcanoes offer such direct access to their internal behavior. For much of the 20th and early 21st centuries, Poás was famous for its crater lake, Laguna Caliente, one of the most acidic natural lakes on Earth. At times, the lake's pH has dropped close to zero, comparable to battery acid. Its color shifts dramatically depending on chemical composition, from milky gray to vivid turquoise or green. The lake exists because rainwater accumulates in the crater faster than it can drain. This water interacts with volcanic gases, particularly sulfur dioxide, hydrogen sulfide, and carbon dioxide. These gases dissolve into the water, forming sulfuric acid and other corrosive compounds. The result is a lake that actively dissolves rock. Bubbles constantly rise to the surface as gases escape. Mud pots forms along the edges. Occasional explosions of steam and ash occur when gas pressure builds beneath the lake, ejecting water and debris into the air. At times, activity increases enough to cause the lake to evaporate or be expelled entirely. When this happens, the crater floor is exposed, a chaotic landscape of steaming vents, unstable ground, and sulfur deposits. These cycles, lake formation, acid concentration, disappearance, and return, are a defining feature of Poás. Unlike calm crater lakes that persist for centuries, Laguna Caliente is temporary. Its existence depends on a delicate balance between rainfall, evaporation, and volcanic heat. Any change in that balance reshapes the crater. Poás has a long history of eruptions, some subtle, others violent. Historical records describe activity as early as the 18th century. In more recent times, eruptions have included ash plumes rising kilometers into the air, ballistic rocks ejected from the crater, and widespread gas emissions. Between 2017 and 2018, Poás entered a particularly active phase. Powerful phreatic eruptions, driven by the interaction of water and magma, sent ash columns high into the atmosphere. Explosions ejected rocks weighing several tons. Acid rain damaged vegetation in surrounding areas. As a result, the national park was closed for more than a year to protect visitors. When it reopened, access was strictly limited, with time-restricted viewing, gas monitoring, and mandatory safety protocols. These closures highlighted a reality that has always defined Poás. It is not a passive landmark. It is a living system. The volcano's gases are among its most dangerous features. Sulfur dioxide and carbon dioxide can accumulate rapidly, especially under low wind conditions. In high concentrations, these gases are lethal. Even moderate exposure can irritate lungs and eyes, making long stays near the crater impossible during active periods. Vegetation around the crater reflects this hostility. Trees, closest to the rim, are often stunted or dead, their leaves burned by acid rain. Farther away, cloud forest thrives, lush, green, and dense, fed by constant moisture and volcanic soils rich in minerals. This sharp transition from life to lifelessness occurs over surprisingly short distances. Beyond the main crater, Poas contains several other volcanic features, including secondary craters and older eruption sites. One of these holds Laguna Botos, a cool, freshwater lake formed in an extinct crater. Unlike Laguna Caliente, Laguna Botos is calm, neutral, and surrounded by vegetation, a stark contrast that illustrates how dramatically volcanic activity can vary even within the same system. For scientists, Poas is invaluable. Its frequent activity allows researchers to test eruption forecasting models and study the chemistry of volcanic gases in lakes. Changes in lake temperature, color, and acidity often precede eruptions, providing clues about magma movement below. Poas has also contributed to understanding how volcanoes interact with water, a key factor in explosive eruptions worldwide. When magma heats groundwater or crater lakes, pressure can build rapidly, producing violent steam-driven explosions even without fresh magma reaching the surface. This makes Poas particularly dangerous, but also particularly informative. Human interaction with Poas reflects both fascination and caution. Indigenous peoples were aware of the volcano long before modern science. Later, settlers and travelers were drawn by its visibility and accessibility. In the 20th century, Poas became a major tourist destination, allowing people to stand safely, at times, just meters from an active crater. Few volcanoes in the world offer such proximity. This closeness has shaped public perception of volcanoes as both awe-inspiring and manageable. Yet Poas regularly reminds observers that control is an illusion. Access is granted only when conditions allow, and revoked without hesitation when danger increases. Climate change adds another layer of complexity. Shifts in rainfall patterns could affect crater lake formation and stability. Changes in atmospheric conditions influence gas dispersion. While climate does not cause eruptions, it can affect how volcanic systems express themselves at the surface. The future behavior of Poas remains uncertain, as it always has. Some years may pass quietly, marked only by steam and sulfur smells. Others may bring sudden explosions, ashfall, and renewed closures. The crater will continue to change shape, deepen, refill, and empty. What makes Poas compelling is not a single dramatic event, but constant instability. There is no final form to this crater, no equilibrium state. It is a place defined by transition, between water and rock, calm and violence, visibility and concealment. Standing at the crater rim during a quiet moment, it is easy to forget this. The lake may appear still, steam may rise gently, clouds may drift past, softening the scene. But beneath that surface, magma moves, gases accumulate, and pressure builds. Poas is never truly silent. Its sounds are subtle, hissing vents, distant rumbles, the occasional crack of shifting rock. Its movements are slow until they are not. Change here can be sudden and irreversible. In Costa Rica, a country shaped by volcanoes, earthquakes, and rainforests, Poas stands as one of the clearest reminders that the ground itself is alive. It is not a relic of past eruptions. It is not a monument to ancient fire. It is an active system, expressing the ongoing collision of tectonic plates beneath Central America. The crater of Poas does not settle into calm. It does not preserve a single shape. It does not promise safety. Instead, it offers something rarer, a chance to witness a volcano in motion, reshaping itself again and again, in full view. A crater that fills, empties, and fills again. A lake that burns instead of cools. A mountain that never finishes becoming what it is. At Poas Volcano, the earth does not rest, it breathes. The mountains that look painted. In the remote northeast of Western Australia, far from cities, highways, and permanent settlements, a range of hills rises from the savanna in shapes that appear almost artificial. Rounded domes cluster tightly together, their surfaces banded in alternating stripes of black and orange. From above, they resemble giant beehives or coiled stacks of stone. From the ground, they feel ancient, massive, and silent. This is the Bungle Bungle Range, one of the most visually distinctive geological landscapes on Earth, and one of the least understood for much of modern history. The Bungle Bungle Range lies within Purnululu National Park, in the Kimberley region of Western Australia. The range stretches roughly 45 kilometers and rises up to 578 meters above the surrounding plains. Despite its striking appearance, the Bungle Bungle Range remained virtually unknown to the wider world until the late 20th century, hidden by its isolation and the difficulty of access. What makes the Bungle Bungles remarkable is not just how they look, but how they formed, and how long that process took. The story of the Bungle Bungle Range begins deep in geological time, long before Australia took its present shape. The rock that forms these domes is sandstone, deposited approximately 350 million years ago during the Devonian period. At that time, this region lay near the edge of an ancient ocean. Rivers flowing from distant highlands carried sand and sediment into shallow basins, where it settled layer by layer. Over time, these sediments were compacted and cemented into solid rock. For millions of years, the sandstone remained buried beneath additional layers. Later, tectonic uplift raised the land, exposing the rock to erosion. What followed was not rapid destruction, but an extraordinarily slow sculpting process driven by water, temperature, and gravity. The beehive shapes of the Bungle Bungles are the result of differential erosion. The sandstone is intersected by vertical joints, natural fractures formed as the rock cooled and contracted. Rainwater exploited these joints, seeping into cracks and slowly dissolving and washing away material. Over immense spans of time, erosion rounded the edges between joints, isolating individual towers and domes. Unlike sharp pinnacles or cliffs, the Bungle Bungles eroded into smooth, bulbous forms. Each dome is separated from its neighbors by narrow gullies and deep chasms, some only a few meters wide, but tens of meters deep. These corridors channel water during seasonal rains, accelerating erosion while keeping the domes intact. The distinctive striping of the domes adds another layer of complexity. The orange bands are caused by iron oxide, rust, within the sandstone. The black bands are formed by cyanobacteria, microscopic organisms that live on the rock surface. During the wet season, these bacteria thrive, forming thin, dark crusts. During the dry season, they become dormant. This biological layer protects the rock beneath from erosion. As a result, the black bands erode more slowly than the orange ones. Over time, this contrast sharpens the striped appearance, locking the pattern into the landscape. The stripes are not painted, they are alive. This interaction between geology and biology is one of the reasons the Bungle Bungle Range looks so precise and deliberate. The domes are not uniform by chance, they are shaped by a balance between rock composition, fracture patterns, rainfall, and microbial life. The climate of the Kimberley plays a critical role. The region experiences extreme seasonality. For much of the year, conditions are hot and dry. Then, during the wet season, intense monsoon rains arrive, dumping large amounts of water in short periods. These floods carve through the range, deepening gorges and washing sediment away. In the dry months, erosion slows almost to a halt. This stop-start rhythm allows forms to develop gradually without collapsing entirely. One of the most striking features within the range is Cathedral Gorge, a vast circular amphitheater carved into the sandstone. Steep walls rise on all sides, enclosing a space that amplifies sound and holds water after rains. The gorge demonstrates how erosion can hollow out rock from within, creating spaces that feel architectural despite their natural origin. For tens of thousands of years, the Bungle Bungle Range was known to Aboriginal peoples of the region. The area holds deep cultural significance for the traditional owners, including the Kija and Jaru peoples. The domes, gorges, and waterholes are embedded in dreaming stories, law, and seasonal movement across the land. To Indigenous Australians, this landscape was never hidden. Its meanings were understood through story, travel, and experience. Knowledge of water sources, safe pathways, and seasonal change was passed down across generations. What remained hidden was the range's presence in the modern imagination. Because of its remote location and the lack of major infrastructure, The Bungle Bungles were not widely documented by non-Indigenous Australians until the 1980s. Aerial surveys and photographs revealed the full scale of the formation, sparking interest and leading to its recognition as a national park in 1987. In 2003, Purnululu National Park was designated a UNESCO World Heritage Site, recognized for both its geological significance and its cultural importance. Despite this recognition, access remains limited. Reaching the Bungle Bungles requires traveling long distances over unsealed roads that are often impassable during the wet season. Many visitors arrive by small aircraft or helicopter, which offer views that reveal the full geometry of the range. From the air, the domes appear tightly packed, their stripe patterns repeating with subtle variation. The scale becomes apparent only when shadows reveal the depth of the chasms between them. On the ground, movement is slower and more immersive. Trails wind through narrow passages, open suddenly into broad spaces, then close again. Light filters down between domes, changing constantly as the sun moves. Temperatures here are extreme. Summer heat can be intense, while nights can cool rapidly. Water is scarce outside the wet season. Survival in this environment requires knowledge, preparation, and respect for the land. Scientifically, the Bungle Bungle Range offers insight into long-term landscape evolution under stable tectonic conditions. Unlike regions shaped by recent uplift or volcanic activity, the Kimberley has remained relatively stable for hundreds of millions of years. This stability allowed erosion to dominate, refining forms slowly rather than destroying them. The range also demonstrates how biological processes can influence geological outcomes. Without cyanobacteria, the domes would erode more quickly and lose their striped appearance. Life here is not just adapting to the landscape, it is shaping it. Erosion continues today. Every wet season removes a small amount of rock. Every dry season pauses the process. Over geological time, the domes will eventually collapse and flatten, their distinctive shapes lost. But that time lies far beyond human scales. For now, the Bungle Bungles remain one of the clearest examples of how patience can sculpt stone. They show that landscapes do not need dramatic events to become extraordinary. They need consistency, repetition, and time. Standing among the domes, the silence feels deliberate. Sound is absorbed by stone and distance. Wind moves lightly through the gullies. The land feels settled, as if it has reached a form it intends to hold for a while. The Bungle Bungle Range does not overwhelm with a height or violence. Its power lies in pattern and persistence. It reveals how simple materials, sand, water, microbes, can combine to produce forms that feel intentional. These mountains were not carved by a single flood. They were not raised by a single eruption. They were shaped by millions of small moments, repeated without urgency. In the Kimberley, where heat, rain, and stone interact on ancient ground, the Bungle Bungles stand as evidence that the earth does not always need force to create wonder. Sometimes it only needs time. The crack where two worlds drift apart. In a quiet valley in southwestern Iceland, there's a place where the ground itself has opened into a narrow, water-filled corridor. Dark rock walls rise on either side, polished smooth by time and water. The space between them is narrow enough to touch both sides at once. Below the surface, the water is so clear it barely feels present at all. This is Silfra, a fissure where two continents are slowly pulling away from each other, visible not through maps or instruments, but through open space. The Silfra Fissure lies within Thingvellir National Park, a UNESCO World Heritage Site and one of Iceland's most geologically and historically important locations. Silfra is part of the Mid-Atlantic Ridge System, where the North American and Eurasian tectonic plates meet and slowly separate. Here, that separation is not theoretical. It is physical. The plates are drifting apart at a rate of roughly 2 centimeters per year. That movement creates tension in the Earth's crust, which fractures over time. Silfra is one of those fractures, a rift opened by tectonic forces, then filled with water filtered through lava rock over decades. Unlike most places where tectonic boundaries lie deep beneath oceans or buried under kilometers of rock, Iceland exposes this process at the surface. Silfra is one of the only places on Earth where it is possible to see and enter the boundary between two continental plates. The fissure itself formed relatively recently in geological terms. It opened after a series of earthquakes in the late 18th century, particularly following seismic activity in 1789. As the ground shifted, cracks widened, and groundwater began to fill the space. But the water inside Silfra does not come from nearby rivers or rainfall pooling at the surface. It comes from Langjökull, Iceland's second largest glacier. Meltwater from the glacier travels underground through porous lava fields for decades, sometimes up to 100 years, before emerging at Silfra. Along the way, the water is naturally filtered by volcanic rock, removing sediment and impurities. By the time it reaches the fissure, it is among the clearest freshwater on Earth. Visibility in Silfra can exceed 100 meters. This clarity creates an unusual sensory experience. When submerged, depth becomes difficult to judge. Objects appear closer than they are. Walls seem to float. The boundary between water and air becomes almost invisible. The temperature of the water remains constant year-round, hovering around 2 to 4 degrees Celsius. Even in summer, the water is near freezing. Even in winter, it does not freeze, kept liquid by constant flow and geothermal conditions. The fissure is divided into several sections, each with distinct characteristics. Silfra Hall is wide and spacious, allowing light to penetrate deeply. Silfra Cathedral is narrower and taller, with vertical walls that create a sense of enclosure. Silfra Lagoon opens into a broader area where the fissure softens and the walls recede. Each section reflects a different stage of tectonic movement and erosion. Some areas are sharply defined, showing recent fractures. Others are rounded, shaped by water movement and minor collapses over time. The rock walls themselves are basalt, dark volcanic stone formed by ancient lava flows. These rocks record Iceland's volcanic past, layered and fractured by repeated eruptions. As the plates move, new cracks form and existing ones widen. Silfra is not static. Earthquakes continue to affect the area. Small tremors can subtly alter the fissure's shape, opening new passages or closing old ones. Over time, Silfra will change, just as it has since its formation. Eventually, it may drain, collapse, or shift beyond recognition. From a scientific perspective, Silfra is invaluable. It provides direct access to a continental rift zone, allowing geologists to study plate tectonics in real time. Measurements of movement, stress, and deformation here help refine models of how continents split and oceans form. The Mid-Atlantic Ridge, which runs through Iceland, is responsible for the creation of new crust. As plates separate, magma rises to fill the gap, solidifying into new rock. While Silfra itself is not filled with magma, it exists because of this larger process operating beneath Iceland. In millions of years, continued separation along this ridge will widen the Atlantic Ocean further. Iceland itself may eventually split or change shape dramatically as new crust forms. Silfra is a glimpse of that future. Despite its geological significance, Silfra is also known for something unexpected: human access. It is one of the only places in the world where people can snorkel or dive between two continental plates. This activity is tightly regulated to protect both visitors and the environment. Access requires permits, guides, and strict rules. Touching the rock walls is discouraged. Kicking sediment is prohibited. The ecosystem is minimal and fragile. Life in Silfra is sparse. The cold, nutrient-poor water supports little biological activity. Algae grow thinly on some surfaces. Small invertebrates exist in limited numbers. Fish are rare. This absence of life contributes to the sense of emptiness. Silfra feels less like a habitat and more like a space, defined by structure rather than occupation. Sound behaves differently underwater here. Movements feel muted. Bubbles rise slowly. The silence is profound, broken only by breathing equipment and the faint movement of water. Light filters down from above, refracting through crystal clear water and illuminating the rock walls in shades of blue and gray. The effect changes with weather and time of day. On bright days, the fissure glows. On overcast days, it becomes darker, more introspective. Above water, Thingvellir carries its own weight of history. This valley was the site of Iceland's first parliament, the Alþingi, established in the year 930 CE. For centuries, people gathered here to make laws, settle disputes, and govern. The choice of location was practical and symbolic, a central meeting place shaped by geology. The same forces that pulled continents apart also created a natural amphitheater for human governance. Standing at Silfra, it becomes clear how closely Iceland's identity is tied to geology. Volcanoes, glaciers, earthquakes, and rifts are not distant phenomena here. They define the land and shape daily life. Silphra makes this connection visible. Climate change introduces new uncertainties. Changes in glacier melt rates could affect water flow into the fissure. Increased melt could alter temperature, clarity, or stability. Earthquakes could accelerate widening or cause collapse. For now, Silphra remains remarkably stable, maintained by constant water flow and careful management. Its clarity is not guaranteed forever. The fissure also challenges perception. We are accustomed to thinking of continents as solid and permanent. Silphra shows that they are neither. They move, stretch, and fracture continuously, even if we rarely notice. The space between the plates is not dramatic in size, just a few meters wide, but its implications are vast. This narrow gap represents forces powerful enough to reshape oceans over geological time. Silphra does not erupt. It does not collapse suddenly. It does not announce itself loudly. Its significance lies in quiet separation. Over time, the walls will drift further apart. New fissures will form, old ones will change. The valley will continue to widen, millimeter by millimeter. Silphra is a reminder that the Earth's surface is not fixed. Even the ground beneath our feet is in motion. To enter Silphra is to enter a boundary, not just between continents, but between perception and reality. It is a place where abstract concepts become tangible. You can reach out and touch North America with one hand. You can touch Europe with the other. Between them, water flows. Cold, clear, patient. The fissure doesn't care who observes it. It does not respond to presence. It continues to widen, slowly and relentlessly, as it has since it opened. In Thingvellir, where history and geology intersect, Silphra stands as one of the clearest demonstrations that the Earth is still unfolding. Not violently, not dramatically, but steadily, pulling itself apart 1 centimeter at a time. The volcano that speaks every night. On the island of Tana, in the southern Pacific Ocean, there is a volcano that almost never falls silent. Every few minutes, the ground trembles. A deep, hollow boom rolls across the land. Red-hot fragments arc into the sky, briefly illuminating clouds before falling back into the crater. This is not a rare eruption or an unusual event. This is normal. This is Mount Yasur, one of the most continuously active volcanoes on Earth, and one of the few places where volcanic power can be witnessed directly, repeatedly, and predictably. The Mount Yasur rises only about 361 meters above sea level, making it modest in height compared to many famous volcanoes. Yet, its influence extends far beyond its size. For more than 800 years, Yasur has been erupting almost continuously, making it one of the longest-running active volcanoes known to science. What makes Mount Yasur extraordinary is not scale or destruction, but persistence. To understand Yasur, it is necessary to understand where it stands. Vanuatu lies along the Pacific Ring of Fire, a massive zone of tectonic activity encircling the Pacific Ocean. Here, the Australian plate is being forced beneath the Pacific plate in a process called subduction. As the descending plate sinks into the mantle, it melts, producing magma that rises toward the surface. Mount Yasur is one of the surface expressions of this deep, ongoing collision. Unlike volcanoes that store pressure for centuries before releasing it in catastrophic eruptions, Yasur operates differently. It is an open vent volcano. Gas, magma, and pressure are released regularly through multiple vents, preventing long-term buildup. This constant release produces frequent, smaller eruptions rather than rare, massive ones. The result is a volcano that behaves almost like a heartbeat. Every few minutes, magma rises near the surface. Gas pressure builds briefly. Then an explosion occurs, ejecting lava bombs, ash, and gas into the air. The cycle repeats again and again, day and night, year after year. This type of activity is known as Strombolian eruption behavior, named after Mount Stromboli in Italy. Yasur is one of the clearest and most consistent examples of this eruptive style in the world. The crater of Mount Yasur is broad and shallow, containing multiple active vents. These vents shift over time. Some become more active, others quiet down. New openings form. Old ones collapse. The overall structure changes subtly but constantly. From the crater rim, the interior looks raw and exposed. There's no calm lava lake here. Instead, the surface churns invisibly below, announcing itself only through sound and sudden bursts of light. At night, the effect is dramatic. Each eruption briefly lights the crater walls in orange and red. Clouds glow from below. Ash particles sparkle as they fall. The darkness between eruptions makes each explosion feel sharper, more deliberate. Despite its constant activity, Mount Yasur is considered relatively accessible. Visitors can approach the crater rim, sometimes standing only a few hundred meters from active vents. This proximity is rare among volcanoes, and has made Yasur one of the most observed active volcanoes on Earth. But accessibility doesn't mean safety. Yasur regularly ejects volcanic bombs, chunks of molten or semi-molten rock that can weigh several kilograms. These projectiles can land far from the vents, especially during periods of increased activity. Ashfall can reduce visibility and irritate lungs. Toxic gases, including sulfur dioxide, are always present. For this reason, access is controlled and conditions are monitored. Activity levels are assessed regularly, and safe zones shift depending on eruptive behavior. Even so, the volcano remains unpredictable within its predictable rhythm. For the people of Tana, Mount Yasur is not merely a geological feature, it is a presence. Indigenous Ni Vanuatu communities have lived on Tana for thousands of years. Their relationship with Yasur is woven into daily life, belief, and identity. The volcano is not viewed as a threat to be avoided, but as a powerful entity to be respected. Local belief systems interpret Yasur's eruptions as communication. The sounds and rhythms of the volcano are read as signs, messages reflecting balance, warning, or approval. Rituals and traditions evolved alongside the volcano's activity, not in opposition to it. Villages exist surprisingly close to the volcano. Fertile volcanic soils support agriculture, crops grow well in ash-enriched ground. Life continues with an understanding that the volcano will always be there. This coexistence challenges modern perceptions of volcanic risk. Where many societies seek distance from danger, communities around Yasur have adapted to constant activity, integrating it into their worldview. From a scientific standpoint, Mount Yasur is invaluable. Its consistent eruptions allow volcanologists to study eruption mechanics in near real time. Seismic instruments, gas sensors, and visual monitoring track changes in behavior. Because Yasur rarely goes completely quiet, it provides continuous data on how magma moves and how pressure is released. One of the most studied aspects of Yasur is its infrasound, low-frequency sound waves produced by eruptions. These sounds travel long distances and provide insight into explosion strength and vent dynamics. Yasur's regularity makes it a natural laboratory for understanding volcanic acoustics. The volcano also demonstrates how open vent systems regulate themselves. Rather than sealing shut and building pressure, Yasur constantly vents gas, maintaining a dynamic equilibrium. This reduces the likelihood of massive explosive eruptions, but does not eliminate risk. Historically, Yasur has had more violent phases. Records and oral histories describe periods of increased explosivity, larger ash plumes, and stronger bomb ejection. These episodes remind observers that even persistent volcanoes can change behavior. Geologically, Mount Yasur is relatively young, likely forming less than 1,000 years ago. Its youth contributes to its activity. Magma pathways remain open. Conduits are not clogged by solidified rock. Gas escapes easily. Over time, this may change. Conduits can seal. Pressure can build. Activity styles can shift. Yasur's future behavior is not fixed. The surrounding landscape bears evidence of the volcano's influence. Ash layers blanket nearby areas. Lava fragments dot the ground. Vegetation grows unevenly, responding to soil chemistry and ash fall. The coast near Tana shows additional volcanic features. Black sand beaches form from eroded lava, cliffs shaped by both fire and water. Despite its constant eruptions, Mount Yasur has not destroyed the island. Its activity is focused and localized. It releases energy steadily, rather than catastrophically. This balance has allowed human life to persist alongside it. At sunrise, the volcano appears almost calm. Steam drifts gently upward. The crater is visible without firelight. The surrounding land looks ordinary, even peaceful. Then an eruption breaks the silence. This rhythm, quiet, explosion, quiet, defines Yasur. It doesn't build toward a single dramatic event. It repeats itself endlessly, like breathing. At night, the volcano becomes something else entirely. The darkness amplifies sound and light. Each eruption feels closer. The sky reacts. Clouds glow red from below. The ground vibrates faintly underfoot. There's no sense that the volcano is waking up. It never slept. Mount Yasur challenges the idea that natural danger must be rare or extreme to be meaningful. Its power lies in constancy. It reminds observers that the Earth doesn't always release energy in bursts separated by long silence. Sometimes it speaks continuously. In a world where many volcanoes are known only through disaster footage or historical accounts, Yasur offers something different, a chance to witness active geology as a regular process. It's not a spectacle of destruction, it is a system in motion. For scientists, Yasur is a living textbook. For local communities, it is a neighbor. For visitors, it is an encounter with the Earth's inner workings laid bare. The volcano will continue to erupt tomorrow. It will erupt next week. It will erupt next year. Eventually, Yasur will change. It may quiet, it may intensify. It may alter its shape or behavior. But for now, it remains one of the few places on Earth where the planet's internal energy is released openly, rhythmically, and without pause. On the island of Tana, as darkness falls and the first glow rises from the crater, Mount Yasur continues to speak, not in words, not in warnings, but in fire, sound, and motion, reminding anyone who stands nearby that the Earth is not still and never has been. The cave that grew giant crystals, deep beneath the desert of northern Mexico, far below the surface where sunlight has never reached, there is a chamber where crystals grew to impossible sizes. Columns of translucent stone rise from the floor like frozen beams of light. Some are longer than a city bus. Others are thick enough to block entire passages. They intersect at strange angles, filling the space so completely that walking through the chamber is almost impossible. This is the Nika Crystal Cave, a place where geology, chemistry, heat, and time align perfectly to create one of the most extreme mineral environments ever discovered. The Nika Crystal Cave lies about 300 meters beneath the town of Nika in the state of Chihuahua. It is located inside the Nika mine, a working lead, zinc, and silver mine operated for decades. The cave was not known to exist until the year 2000, when miners drilling a new tunnel broke through a wall and exposed a chamber unlike anything seen before. What they found was not a typical cave. There were no stalactites or stalagmites, no dripping water, no flowing passages carved by erosion. Instead, the chamber was filled almost entirely with crystals of selenite, a crystalline form of gypsum, calcium sulfate dihydrate. These crystals were enormous, far larger than any previously known natural gypsum crystals. Some measured more than 11 meters in length and weighed up to 55 tons. To understand how this happened, it is necessary to look far beyond human timescales and deep into the geological history of the region. The Nika region sits above a complex system of magma intrusions left behind by volcanic activity millions of years ago. These intrusions heated surrounding rock and groundwater, creating a long-lived hydrothermal system beneath the surface. For hundreds of thousands of years, possibly more than 1 million, the cave existed not as an air-filled space, but as a sealed chamber filled with hot, mineral-rich water. Temperatures inside the chamber remained remarkably stable, hovering around 54 to 58 degrees Celsius. This stability is critical. In most environments, crystals grow quickly and imperfectly. Temperature fluctuations, changes in chemistry, or physical disturbance cause crystals to stop growing or fracture. In Nika, none of this happened. The water inside the chamber was saturated with calcium sulfate, supplied continuously by surrounding rock. At the same time, the temperature remained just below the point at which anhydrite, a different calcium sulfate mineral, is stable. As conditions slowly shifted, anhydrite dissolved and reprecipitated as gypsum. This process happened extremely slowly. Crystals grew not in bursts, but atom by atom, over immense periods of time. With no competition, no disturbance, and constant conditions, a small number of crystals grew uninterrupted, expanding outward in all directions. The result was size without limit. The crystals grew until they collided, with each other or with the cave walls. They did not stop because conditions changed. They stopped because there was no space left. The cave itself is relatively small, roughly the size of a large room, but it feels overwhelming because the crystals dominate every surface. Some grow from floor to ceiling, Others cross the chamber diagonally, forming natural bridges of stone. The clarity of the crystals is equally striking. Many are translucent, almost glass-like. Light passes through them, refracting softly. Their surfaces are smooth, reflecting the absence of erosion or breakage during growth. But this beauty hides an extreme danger. When the cave was first entered by humans, it was filled with air rather than water. This happened because mining operations had pumped groundwater out of the surrounding rock to keep tunnels dry. As water levels dropped, the chamber drained, exposing the crystals for the first time in their existence. The air inside the cave is brutally hostile. Temperatures remain around 45 to 50 degrees Celsius. Humidity approaches 100%. Under these conditions, the human body cannot cool itself through sweating. Heat builds rapidly, leading to hyperthermia. Without specialized cooling suits, a person can survive inside the cave for only 10 to 20 minutes before losing consciousness. Early exploration required full protective gear, insulated suits with ice packs and breathing systems. Even then, visits were brief and dangerous. Scientists worked in shifts measured in minutes, not hours. Despite these challenges, research teams managed to study the cave's crystals, chemistry, and microbial life. One of the most surprising discoveries was biological. Within fluid inclusions trapped inside the crystals, tiny pockets of ancient water sealed during crystal growth, scientists found dormant microorganisms. These microbes had likely been isolated for tens of thousands, possibly hundreds of thousands of years. When reactivated in laboratory conditions, some of these organisms showed signs of metabolic activity. This discovery suggested that life can survive in extreme isolation, high temperature, and mineral-rich environments for extraordinary lengths of time. The Naked Crystal Cave became a point of interest not only for geology, but for astrobiology, offering clues about how life might persist in subsurface environments on other planets or moons. The cave also challenged assumptions about crystal growth limits. Before NACA, crystals of this size were thought impossible under natural conditions. The cave proved that size is not limited by chemistry alone, but by stability and time. Remove disturbance, maintain temperature, allow saturation. Wait, for humans, this is an almost impossible combination to replicate artificially. The cave's discovery sparked global interest, but it also raised immediate concerns about preservation. Once exposed to air, the crystals began to degrade. Changes in temperature and humidity caused dehydration at the surface. Fine cracks appeared. Dust from mining activity settled on crystal faces. Microbial contamination became a risk. To prevent further damage, access to the cave was strictly limited. Eventually, the mine ceased pumping operations, allowing groundwater levels to rise again. As the water returned, the cave began to flood. Today, the Nika Crystal Cave is once again submerged. This flooding may be the only way to preserve the crystals long term, returning them to the environment in which they formed. Hot, mineral-rich water slows degradation and prevents collapse. As a result, the cave is no longer accessible to researchers or visitors. What little humanity has seen exists only in photographs, samples, and scientific records. This makes the Nika Crystal Cave one of the rarest kinds of natural wonders, a place revealed briefly, then hidden again. There's no folklore associated with the cave, no ancient myths, no human stories passed down through generations. For almost all of human history, it didn't exist in our world at all. It grew silently while civilizations rose and fell above it. The desert overhead changed climates. Animals evolved and disappeared. Humans arrived, mined the land, and moved on. All the while, crystals continued growing underground, untouched. From a geological perspective, Naga is a reminder that some of the Earth's most extraordinary processes occur far from the surface, beyond sight and awareness. Landscapes do not only form through erosion and uplift. Some form through stillness. The cave did not require force. It required patience. It is also a reminder of fragility. The conditions that allowed these crystals to grow are rare and easily disrupted. Once altered, they can't be restored on human timescales. The cave's brief exposure may already have caused irreversible changes to some crystals. What remains intact does so only because it has been hidden again. Nika challenges the idea that discovery is always beneficial. In some cases, observation itself is destructive. To see the cave is to change it. This tension between knowledge and preservation defines Nika's legacy. Scientifically, it expanded understanding of crystal growth, hydrothermal systems, and extremophile life. Philosophically, it raises questions about what should remain unseen. The cave does not need visitors to exist. It existed without them for hundreds of thousands of years. Now, it exists again without them. Beneath the town of Nika, below layers of rock and heat, the crystals remain, silent, massive, and growing no longer, but preserved in darkness and water. They do not glitter for anyone. They do not reflect cameras. They do not invite entry. They simply are, monuments not to violence or upheaval, but to the rare moments when the earth remains perfectly still long enough for something extraordinary to grow. In the end, the Nika Crystal Cave is not a spectacle of motion. It is a record of stability, a reminder that sometimes the most astonishing things on earth are created not by change, but by the absence of it. As this journey comes to an end, these places remain, shaped by fire, water, pressure, and time far beyond human scale. They remind us that the earth is never still, only changing in ways we rarely see. Thank you for watching Unearthed Secrets. Until next time, keep looking closer beneath the surface of our world.